Everything from ancient astronomical observations 2,500 years ago to black holes in space. No human endeavor has transformed society and defined our place in the cosmos more than the physical sciences. What started as a kernel of knowledge about the movement of the heavenly bodies has expanded to include the atomic building blocks of all chemistry, geology's understanding of Earth's long history and the forces that have shaped our planet's features, astronomy's picture of an ever-expanding universe populated by billions of galaxies, each containing billions of stars, and physics' understanding of the basic principles of movement, energy, and forces which have given us the technological world of cars, planes, television, computers, cell phones, and the electrification of the planet. Turning Points in the Physical Sciences takes you on an exciting journey of discovery from ancient through classical science to the world of modern physics, relativity, chaos theory, and quantum mechanics. In the 19th century, electricity and magnetism, two of the more mysterious natural phenomena known to ancient cultures, came together in the most surprising way, a way that wholly transformed the world. Most ancient civilizations knew that little magnetic rods, called lodestones, would align themselves on the surface of the Earth, always pointing in the directions of north and south. And the Chinese in 300 AD reportedly made the first compasses for the purposes of navigation by floating these little rods in water. Originally, it was believed that magnetism emanated from the heavens. But in 1600, William Gilbert published De Magnete. In this treatise, he proposed that the Earth itself was a lodestone, a giant magnet. He also described how heating iron while maintaining a north-south direction could make permanent magnets. Indeed, magnets themselves have a north and south pole. Like poles of magnets repel, and opposites attract, producing a remarkably powerful force seemingly out of nothing. Early experimenters also learned that objects could be sorted by whether they were attracted to magnets. By the turn of the 19th century, natural philosophers had demonstrated that magnetism existed as a field of force, seen by spreading iron filings on top of a piece of paper covering a magnet. At the same time, they had learned to produce a steady current of electricity by means of primitive batteries. Was it possible that magnetism and electricity were somehow related? In one of the most dramatic moments in all of science, Hans Christian Ørsted noted during a lecture that a compass needle moved when brought close to a wire carrying an electrical current. On July 21, 1820, he published a 6-page paper describing his discovery. This astonishing breakthrough heralded the birth of electromagnetism and started the obsession with unification of the basic forces in nature, an elusive goal that would drive scientists well into the 21st century. Incredibly, the science of electromagnetism would lead in a few years to the great discoveries of Michael Faraday, who laid the groundwork for the large-scale generation of electricity that lights and powers the modern world. At the start of the 19th century, the steam engine was propelling Western civilization into the Industrial Revolution. Yet scientists really had no idea of the principles that lay behind the working of this marvelous invention. Understanding these basics required a major rethinking of the concept of heat, and resulted in formulating two of physics' most basic laws, the laws of thermodynamics. 18th century chemists held the belief that heat was a kind of fluid contained in all matter. Called caloric, heat flowed from one substance to another. This assumption fit everyday experience. But by the end of the century, it had been observed that heat could be produced by electricity, and heat could also be produced by mechanical actions, such as the boring of a cannon. These observations threw into doubt the old ideas about heat. Men such as the American-born cannon engineer Count Rumford had the profound insight that it was related to energy and doing work. But the question remained, how? The unraveling of this mystery began in 1724, when Fahrenheit invented the mercury thermometer. It provided an accurate way of measuring the temperature of an object. But by the 19th century, scientists asked themselves if they were really measuring heat. The answer was no. This answer changed the course of scientific inquiry and led to the startling discoveries of the 20th century. What early scientists were actually measuring was heat's effect on the mercury. Energy was not being measured directly, only its effect was being observed. This meant that heat, and perhaps all energy, was potential, the potential to do something. Later, more precisely defined as the ability to do work, energy was acknowledged as unobservable by human senses and therefore not physical or material. In a famous experiment of the time, the English physicist James Joule showed that the rate of cranking a paddle could predictably raise the temperature of water in a container. What became important was the ability of scientists to get precise, measurable, and predictable results of energy's effects. This was perhaps the most dramatic conceptual change in all of science. Then by the middle of the 19th century, scientists were looking for the fundamental laws that governed this new concept of energy. At that time, the work of Sadi Carnot, a French engineer working on improving the performance of steam engines, was rediscovered. In 1824, he published Reflections on the Motive Power of Fire. In this paper he stated, work could only be gained from heat by a transfer from a hot to a cold body, just as heat was transferred from the boiler to the condenser of a steam engine. This observation led to the concept that energy, the ability to produce an effect, can neither be created nor destroyed. Carnot came up with the first law of thermodynamics. The total energy of the universe is constant. Additional experiments dramatically showed a corollary, that energy, heat, mechanical, and electrical, could be transformed from one form to the other. For example, mechanical movement was capable of producing both electricity, as demonstrated by Faraday, and heat, as demonstrated by Joule's paddle wheel apparatus. However, it appeared that the first law of thermodynamics allowed for the possibility of perpetual motion machines. 19th century German physicist Rudolf Clausius knew that something more was needed to define thermodynamics. He coined the word entropy to mean the amount of thermal energy not available to do work. Based on the everyday observation that warm objects such as a cup of coffee always spontaneously become colder, Clausius stated the second law of thermodynamics, that the ability of energy to do work is always decreasing. In other words, the universe tends towards maximum entropy. In short, as fellow German physicist Hermann von Helmholtz stated, the universe is dying, and no perpetual motion machine is possible. All at once, our worldview and our place in the universe changed dramatically. What still remained was the discovery of the relationship between heat and atomic movement, but the new understanding of thermodynamics paved the way for a revolution in inventions that we now take for granted. Besides steam engines, planes, automobiles, and turbines for creating electricity owe their high level of performance to engineering applications of thermodynamic principles. Of all the 19th century scientific debates, none was more hotly contested than, how old was the Earth? And how did the surface come to be as it is? How did it come to be a patchwork of mountains, badlands, flat plains, hills, rivers, lakes, and oceans? In his seminal publication, Principles of Geology, Charles Lyell answered the second part of the debate, and in doing so laid the foundation for all future Earth sciences. To ancient cultures, the Earth was like a stage, a place laid out once and for all by God, on which the human drama would play itself out. However, by the end of the 18th century, natural scientists took a different view, prompted by a growing fossil record that revealed creatures that no longer existed. In addition, Scotsman James Hall and other geologists were performing laboratory experiments that produced crystals under controlled conditions. They also used intense heat to create a wide variety of rock types. To their mind, the Earth's surface must have resulted from some natural process. But what was it? Before Lyell's publication in 1830, there were two competing scientific theories for what this process was. One, the Neptunus theory, named after the Roman god of the sea, held that the Earth was totally covered by water, and its features resulted from the recessions of the floodwaters. The other, the Plutonist, named after the Roman god of the underworld, advanced the idea that the Earth's features resulted from a cataclysmic event of intense heat and pressure. Rather than searching for a one-time event, Lyell argued that geology should look to the forces in play today. What was happening now was the key to what happened in the past. This theory had the odd name, uniformitarianism. Uniformitarianism, while not answering the age of the Earth's crust, clearly showed that these forces worked slowly today, and therefore the Earth must be very old to produce the dramatic physical features found across the planet. In time, additional forces such as glaciation and continental drift would be added to the actions that shaped the Earth's surface. But in 1830, Charles Lyell got it right and forever changed the study of geology. As for the age of the Earth, it would take another 100 years to get the answer. 4.5 billion years old. Michael Faraday was one of the greats of physics, standing like a guidepost between Newton and Einstein. Unlike most of his contemporaries, he was primarily interested in the why of his experiments. In 1822, he made a diary entry for himself: convert magnetism into electricity. 9 years later, he did just that, with the principle demonstrated here. Late 18th century experimental scientists were beginning to believe everything was electrical, a truth that would be borne out 200 years later. Public lecture shows were the reality TV entertainment of the day. Though the demonstrations were sensational, few believed anything practical would ever come of these delightful phenomena. However, the unification of magnetism and electricity would soon change this attitude. It was a unification that began in 1821, when William Sturgeon built the first electromagnet by wrapping an iron core with copper wire and attaching the leads to a battery. This electromagnet had all the properties of natural lodestones. Sturgeon also made the first electric motor. Using the principle that magnets push and pull each other, he constructed an apparatus that looked something like this. When the switch was thrown, the copper wire became an electromagnet that spun around by the push and pull of the permanent magnets. This simple motor is virtually identical to the ones found everywhere in the home today. Fans, vacuum cleaners, washers, and dryers. And the list goes on. Like the home user of motors, Sturgeon was not concerned with how his inventions worked as long as they did what they were supposed to do. But Michael Faraday was a different kind of scientist and inventor. He wanted to know how these forces worked and why they did what they did. In 1831, Faraday fulfilled his own directive of 9 years earlier when he discovered electromagnetic induction. With an experimental setup like this one, he produced electricity from magnetism. When the magnet passed through the copper coil, for a brief moment the needle tipped in one direction and then went back to zero. Moving back in the other direction once again produced the tip of the needle also in the opposite direction. Electricity was being produced. How could this be? And why was there only electricity for a brief moment? With startling intuitive reasoning, Faraday hypothesized that the movement of a conductor through a magnetic field was the important factor. Send a coiled wire back and forth through a horseshoe magnet, and the bulb lights up like the one shown here. Faraday was right. It's the movement through the magnetic field that produced his experimental results. In another of Faraday's experiments, the expansion and contraction of the magnetic field produced electricity in an adjacent wire. Amazingly, in that very simple setup, Faraday had in fact built the first electrical transformer. Transformers that were not significantly different from the ones that dot the landscape in every developed country today. A year later, Faraday produced an even more spectacular application of electromagnetic principles, Faraday's dynamo or electric generator. By taking a permanent horseshoe magnet and cranking a copper disc through the magnetic field, Faraday was able to generate a steady electrical current. Again, this setup was not significantly different from what is found in a modern power plant. Faraday then went on to state, the faster the turning, the bigger the magnet, the more coiling of the wire, the more electricity that can be produced. A modern power plant does just that. It converts mechanical movement powered by heated water to spin an enormous coil of wire inside a giant magnet. In electrical generation of power, bigger is indeed better. Faraday's discoveries and laws set the stage for the era of electrical inventions 50 years later, and the insatiable consumption of electricity by the industrial and post-industrial ages. Equally as important, Faraday laid the foundation for the unification of electricity and magnetism, a unification that would be simplified by the Scottish physicist James Clerk Maxwell. Naturalists who traveled to high mountain ranges were well aware of glaciers and their powerful effects as they moved across the landscape. Early in the 19th century, geologists knew of boulder fields containing rocks from nearby mountains and huge gravel deposits far from any rivers called drumlins. But how could that be? In 1837, a Swiss-born pastor, Louis Agassiz, presented what he called the discovery of a great ice age to the Swiss Society of Natural Scientists. He argued that a massive ice age had wiped out the megafauna of mastodons, mammoths, saber-toothed tigers, and other large animals found in the recent fossil record. While incorrect in his argument, his idea of an ice age was indeed true. In fact, for the million years of human existence, the climate has been highly volatile. During that time, the planet has experienced 4 major glaciations of the northern hemisphere. The last great ice sheets reached into the United States a mere 70,000 years ago. The existence of ice ages raised the question, what factors could cause such dramatic shifts in the climate? The pursuit of an answer led first to the study of atmospheric gases and the discovery of the greenhouse effect in 1863 by the Irish physicist John Tyndall. He found that, although all atmospheric gases are transparent to light, some, like carbon dioxide, are opaque to infrared radiation, thus acting like a warming blanket for the Earth. In short, carbon dioxide traps the thermal energy that would normally bounce back into space. The increased production of carbon dioxide by industrialization may be impacting the climate today, but no such effect was in play 15,000 years ago, so another explanation was needed. Then in 1914, the Russian scientist Milutin Milanovich proposed that large-scale climate changes resulted from the eccentricity of the Earth's own movements, its elliptical orbit around the Sun, its wobble as it spins on its daily cycle, and the shift in its orbital to equatorial plane. These movements occur in cycles and seem to coincide with the waxing and waning of the glacial periods. Milanovich believed that these movements in relationship to the Sun were enough to affect climate shifts, producing the glacial cycle. Over the next 100 years, his ideas would gain greater acceptance. In the 21st century, climatology would become a rich area of scientific study. As for the extinction of the megafauna at the end of the last ice age, it still remains a mystery today. A common experience of the Doppler effect happens when a person stands on the corner when an ambulance or fire truck approaches. Sirens blare. What happens? Not only does the siren get louder, but the pitch also rises. Then after the vehicle passes, the pitch dramatically lowers as the sound diminishes. This shift in the frequency of the sound waves was first put in the form of a principle by Doppler in 1842. He stated that the drop in the pitch of the sound heard was directly proportional to the speed of the object moving away. The study of sound in recorded history dates back to 500 BC, and Pythagoras' fascination with the relationship between the length of the string on a harp and the pitch of a note. He had learned the shorter the string, the higher the note. Sometime in the middle of the 18th century, naturalists using cannon fire were able to get a reasonably close measurement of the speed of sound, now known to be 340 meters per second, or 750 miles an hour at sea level. By the time of Doppler's principle, scientists had discovered that sound took the form of a wave, an expansion and contraction of air. Using a computer model of a wave, with a sound source and a fixed recipient, we can see that the sound moves away from the source in a series of concentric circles in the form of wave fronts. Now, let's put the sound source in motion moving towards the recipient. What happens? The wave fronts begin to bunch up, and the recipient hears a higher pitch. Now let's accelerate the source to the speed of sound. What happens then? The wave fronts become bunched at a point, and the recipient hears nothing until the source arrives. When it does arrive, the recipient experiences an extreme shock wave, the well-known sonic boom produced by supersonic jets. The Doppler effect might have become merely a scientific curiosity, except it was found to apply to the complete range of the electromagnetic spectrum. Using just the visible part of the spectrum, astronomers were able to detect red shifts, indicating low frequency, or blue shifts, signifying high frequency, by the light emitted from astronomical objects such as stars and galaxies. Just as a person could tell by the change in pitch alone if an object was moving towards or away from him, scientists could determine by the color shift if a star is moving towards the Earth or away from it. Red shift meant moving away and blue shift coming towards. The Doppler effect went on to play a major role in understanding the nature of the universe. The Doppler shift was put into practice at the end of the 20th century with the invention of Doppler radar. Sending out radio waves from a transmitter and then recording their echoes, meteorologists were able to measure the velocity and direction of wind in storms. Thus, they are able to see tornadoes and damaging winds from a far distance, enabling them to warn residents in the path of storm.